Hello everyone, welcome to IMS GATE Academy. I am Atul Negi, faculty at IMS GATE Academy. So as you know, we are doing our foundation course in fluid mechanics and we have already completed 2 units. That is properties of fluids we have completed, and after that fluid statics we have completed. And I hope you have learned so many concepts in that particular chapters. Right. So as of now, we are starting our new chapter, that is fluid kinematics. Okay. So till now whatever we have discussed with regarding to the statics condition, when the fluid is under rest condition. Now we will do the analysis of fluid when it is actually moving and when actually it is under motion. Okay. So till now whatever we have discussed, it is under static conditions. Okay. So all those things we are going to discuss again when the fluid is under motion. So we will see what are the differences it will have when the fluid is moving. What are those parameters which are now again involved in this fluid analysis? Previously few parameters involved, now much more parameters now it will involved in the fluid analysis as it is what moving, right? So you should be what aware of the basic fluid properties whatever we have discussed, okay, in the previous lectures. And if you have not watched those lectures, please go and watch previous lectures, because those chapter number 1 and chapter 2 are the basic foundation of the fluid mechanics. So you have to understand the basics, then only you will get to know about how we can do the analysis when it is under actually motion. Okay. Now when I say fluid kinematics, you should understand a very important point, like how it is different from the kinetics or dynamics. Because dynamics basically means the study of a object which is under motion, and under dynamics only the kinematics and kinetics will come. Now you should be aware of, like when I say fluid kinematics, which of the things we need to do as analysis, which of the things we need to look for as far as analysis is concerned, right? So those things I will be discussing in this particular lecture, and apart from that types of fluid flow and fluid flow pattern I will be discussing. Okay, types of fluid flows are there, flow patterns, those particular things I will be discussing, right? So now fluid kinematics. So you should aware of, like when I say kinematics, which of the parameters I need to look for. Okay, so when I say kinematics, you should understand, obviously motion will be there, but what are the parameters? That is what very important. So when I say motion, the first thing that come into your mind is what? There should be some displacement. There should be what? Change in the position of that particular element or any body or any particle. Change of the position will be there, right? If it is a particle or body, it doesn't matter, but as far as the motion is concerned, it means change of the position. So when the position is changing, it means what? The motion is there. Okay, now you should understand, like motion everyone knows. Okay, first of all, when I say motion, you should understand like change of position. Change of position. So now when change of position is there, you should understand there will be some displacement. So there will be some velocity associated with that particular displacement. There will be some acceleration associated with that. There will be some momentum associated with that. So all those basic things, basic parameters which are actually what directly involved with the motion, those parameters I will be discussing in this fluid kinematics. So when I say analysis of fluid flow, I will be what restricting myself with regards to those parameters which is what directly related to the motions, right? So I am just concerned about the motion only. I am not concerned about the reason. Why? Because what is the reason of motion? I will not concerned about that. I will just concerned about the motion related parameters. Okay, we don't need to worry about how the motion is happening here. What is the reason of motion? We don't need to go for those reasons. Okay, we'll do that analysis in fluid dynamics chapter. That is again a separate chapter. After this fluid kinematics, I will be taking fluid dynamics also. But as far as this fluid kinematics is concerned, we need to what? Restrict ourselves with regards to motion related parameters, right? So when I say motion, change of position, so it means what? position analysis we need to do. Position analysis we need to do, right? Sir, fluid kinematics is a little bit hard topic. See, it is hard if you don't know the basic understanding of the mathematics, right? So don't worry about that. We'll discuss all the basic things regarding mathematics part, which is what very much involved in this kinematics. We'll discuss all those mathematics portions also. Right. So first of all, understand motion. It means change of position. Next, and change of position is there. Obviously, some displacement you can expect. You can expect the displacement. Right. So from the displacement, I can get to know about the velocity. And from the velocity, I will get to know about the acceleration. So that's how the different parameters are linked. Right. And from the displacement, I can get to know about velocity. So understand first of all what is motion, change of position, and from that displacement, and from that velocity, and from that acceleration, right? So like that you should aware of the parameters. I hope the point is clear, everyone. Now in whole kinematic chapter, fluid under motion, you should always calculate what is the velocity, what is the acceleration, okay, what is the position of the fluid particle when it is under motion. All those parameters I will be doing as an analysis in this particular chapter, right? So I hope the point is clear, everyone. So what are those parameters I need to look for in this fluid kinematic analysis, right? So when I say fluid is under motion, obviously some reasons are involved, okay, but don't consider those any forces. Let's suppose any forces are involved or whatever the reason is there for the fluid motion, we don't need to worry about those things. We'll discuss the forces in the next chapter, that is dynamics. So actually why it is important to study first of all motion, then after that forces. Very important questions. Most of the time students will ask her why we are studying first of all motion then forces, because the motion is happening because of some force only. So why should not we discuss force first of all, then this motion related parameters? That is what pretty much obvious thing, right? Because some forces are acting on the fluid, then only it is what moving. And sir, you are studying about the motion first of all, then after that force. So that is what the frequently asked question by the students in the classroom. Now you should be aware of, like, let's suppose if I basically ask you, let's suppose how you will calculate the force. How you will calculate the force, right? So basically the first formula come into your mind is what? Newton's second law, that is mass into acceleration. See, mass we anyhow know, but in order to calculate the force, you need to know about the acceleration. That is what required in order to calculate the force. And again, in order to calculate the acceleration, you need to know about the velocity. And in order to calculate the velocity, you need to know about the displacement. And in order to calculate this displacement, you need to know about the position. Are you getting the point what I'm trying to say here? Like obviously because of the some forces acting on the fluid element, because of the forces only it is what moving. So why we should not study the first of all forces then the motion? We are studying the motion because of the reason that we can easily calculate, we can easily measure these particular parameters: position, displacement, velocity and acceleration. And because of these parameters only I can calculate the force also. Without these parameters, without the understanding of these parameters, I cannot calculate the force. That is what a very important point. So that's why we always do the analysis with respect to kinematics, then after that we'll do the dynamics. So that is what also applicable in engineering mechanics. So first of all we will study kinematics and after that we'll study the dynamics. And again same thing happens in the subject theory of machine. Mechanical engineering student knows that. First kinematics of machine they will study and after that they will study dynamics of machine. So this relation should be what clear to everybody. Okay, I hope the point is clear, everyone. Now next thing. So when I say doing the analysis, there are two different approaches. Okay, so first approach is the Lagrangian approach and second approach is the Euler approach. Okay, so I will tell you the basic difference between Lagrangian approach and the Euler approach. Okay. Now you should understand what is the basic difference between this Lagrangian approach and Euler approach. So as far as this point is concerned, like Lagrangian approach, again Lagrangian is basically the scientist, Euler is also the scientist. Based on their philosophies, based on their approach, two different analysis, two different approaches for the analysis has been there. Now you should understand the basic difference. When I say Lagrangian approach, in this Lagrangian approach, what is the basic thing? The thing is that we need to focus on the each particular molecule. Let's suppose any particle you have taken, and for that you are doing the analysis. What is the motion, how it is moving, what is the velocity, what is the acceleration? You are just basically tracing the motion of any particular particle. Are you getting the point? So let's suppose there is one particle in the fluid flow. Obviously, when the fluid is flowing, n number of particles are there, right? So now you are just focusing on any one particular fluid particle, and throughout its journey, you are just tracing its movement, right? You are just tracing its movement. So let's suppose this is the path. So you are observing the particle, fluid particle, throughout its journey. So this is, let's suppose, the path with that it follows during its journey. So during the motion, you should understand, like velocity will be there, acceleration will be there. Okay, change of position, obviously it will be there because it is under motion. So you will be focusing on each and every particle. So in order to analyze, you have to focus on every particle. But literally, it is practically impossible to focus on each and every particle, right? It is very difficult. Because if I say, let's suppose there is some mass of fluid is there, obviously n number of particles are there. So n number of times I need to focus on each and every particles. So again, it becomes a very complex process. See, it will be applicable only under certain conditions when the number of fluid particles are very less. Number of fluid particles are very less. In that particular condition only it is possible. Otherwise it is very difficult, right? So this is the basic disadvantage we are having with regards to the Lagrangian approach. Now coming to this Euler approach, as the fluid is flowing, okay, as the fluid is flowing, there will be some flow field will be there, and as the fluid is flowing, at every certain points, at any point, let's suppose, at any points, some velocities will be there, some accelerations will be there, right? Let's suppose if I have drawn this coordinate geometry in the fluid system, let's suppose this is x, this is y, this is z. Try to understand this point, very important. So let's suppose any coordinate system I have assumed, and there is a flow field here. Now flow field basically means what? At certain points you will be having the velocities and accelerations, right? See, let's suppose if I select this point, so at this point what is the direction of velocity? Let's suppose this is the direction of velocity. At this point, this is the direction of velocity. At this point, this is the direction of velocity. What is the acceleration? So similarly, you can explain other parameters also, like acceleration. So at different points, as the field we are talking about, at different points, you will be having different values, right? So it is better to focus on that particular point, not on the particle. See, as I compare both the approaches, what is the basic difference? Here I am focusing on any particular particle and I will follow that particular particle throughout its journey. But in the case of Euler approach, field approach I will be taking. What is the field approach? A field will be set up within the fluid flow, and at any particular point, the variations of velocity and acceleration I will figure out, and I will analyze those changes in that particular point. I basically focus on any particular point, and at that point I will see the changes in the velocity and acceleration, or with regards to any fluid parameters. So that is what the field analysis, right? I am not focusing on the fluid particle, I am focusing on any particular point in the fluid flow itself, and at that particular point I will be checking the changes in the fluid properties. I hope the point is clear. The difference between Euler and the Lagrangian approach, very important point, guys, very important. Okay, so I will be preferring the Euler approach as compared to Lagrangian approach, but Lagrangian approach will be what useful when the number of particles are what very less. Okay, everyone. But advantage we are getting in Euler approach is the field approach we are taking, and we will stick to any particular point in the field, and I will see the changes. Okay, so this basic difference at least you should know. Okay, now see. So I will be discussing the types of fluid flow. I will be discussing the types of fluid flow because that is what a very important point. During the analysis, various types of fluid flows are there, and we need to know the basic meaning of those flows. Okay, definitely we'll do the analysis, but before going into the analysis, at least we should be aware of the fluid flows. Some certain basic fluid flows we should know. Okay, so certain basic understanding we should be having before going into the exact analysis of the fluid flow. So there are various types of fluid flows, but only few fluid flows I will be taking here because these fluid flows, types of fluid flows are what very important as far as our engineering examinations are concerned, like GATE and PSUs. Right, everyone? I hope up to this everyone is clear regarding whatever we are discussing here regarding fluid kinematics. Now see, so first of all, it is the steady flow. Now again, very basic thing, even in the thermodynamics also you have studied, right? So what is steady flow if I ask you directly? So whenever I ask this point, what is steady flow, everyone say, sir, with respect to time it is constant. What is constant? Let's suppose fluid kinematics we are discussing now. So fluid properties, sir, are constant with respect to time. Is that correct? Yes or no? Is that correct? Like if I ask you what is steady flow, so mostly in the classroom students will say, sir, it is like fluid properties are constant or does not change with respect to time. Is this particular statement is correct? No. Why it is not correct? Why it is not correct? So what part is what missing in the definition? Is anything missing or anything is what wrong I have said? Tell me. So steady flow means the fluid properties do not change with respect to time. You are saying it is wrong according to you. But what is the correct answer then? What is the correct answer? So what is the difference? Actual terms, what is the difference? So if it is not constant with respect to time, then it is what? Having some variation with time. So if it is having a variation with time, then it becomes unsteady flow. Right. So I will tell you the basic difference. So this statement is correct but not complete statement. It is a correct statement but not complete. Why is it so? Fluid properties are constant with respect to time. That is correct, but with respect to fixed location. But with respect to fixed location. With respect to change in the location, properties can change. Right. For example, guys, try to understand. Let's suppose this is the nozzle you are having. Very important point. Very important. So let's suppose this is the nozzle you are having, and in this nozzle the fluid is what passing. From this nozzle the fluid is what flowing. So obviously you can say, sir, at section 2 and at section 1, let's suppose. At section 2 the velocity is what more, as it is what converging, right? Velocity at section 2 will be what greater than as compared to 1, as it is what converging. Now I am saying it is steady flow and you are saying like, sir, the fluid properties do not change with respect to time. Correct. So at any time, at time t equals to t1 if I see, t2 or any time if I see, so values will remain same. But from location to location, velocity values are changing, na? Velocity values are what different according to the location. With respect to time at location 1, velocity will remain the v1 value. With respect to time, velocity value at section 2 will remain v2 forever if it is a steady flow. But from location to location, velocities values will get changed. So when I say steady flow, it means values, fluid property values are constant or do not change with respect to time, but at any fixed particular location. It cannot be like कि everywhere the properties are same. At every location properties are same. It is not like that. Right? So always remember this point, very, very important. Right? So this is the definition that you should remember. The flow in which the fluid properties like velocity, pressure and density do not change with time at fixed location. This point is what very important. You should highlight this point in the definition. Whenever you are writing the definitions, please highlight the most important points. Otherwise, you will remember the main thing only, like do not change with respect to time. But at fixed location, that is also very important point. I hope the point is clear. From location to location, value may change, but with respect to time, at any particular fixed location, values will remain fixed. That is what steady. And opposite to that is what? Unsteady flow. Just opposite to steady will be unsteady. Right? So this point is what very important. So see, property you should understand. There are two difference between property and characteristics. Okay. This point you should understand, like fluid velocity you are saying. See, property can be density, property can be pressure, right? Temperature also. But as far as, let's suppose my system is there, some fluid element I have considered as my system, and if it is moving with certain velocity, I can say this is the characteristics of my system, right? So that point you should remember. Unsteady flow, the flow in which the fluid properties like velocity, pressure and density change with time at fixed location. Right, this point is what very important. At fixed location. At fixed location, values will change. Correct, everyone? Next, so this point at least you should remember. At fixed location point, right? Okay, next, moving on to the next part here. Uniform flow. Again, in this case also, most of the time students face difficulty. Like they remember the basic definition, but actually what is the important point they usually forget. So when I say uniform flow, you should aware of this point, like properties do not change with respect to locations. Properties do not change with respect to location at any particular instant of time. This point is again very important. At any particular instant of time. So for a particular instant of time, properties, fluid properties do not change with respect to location. So everywhere properties are same, but at any particular instant of time. As the time changes, this values will again change, but again it will have same values throughout your system. So this point you should remember. Like if I give you an example here, let's suppose this is the pipe you are having. Right. So let's suppose this is section 1, this is section 2. So velocity V1 equals to V2, let's suppose. Velocity equals to V1. V1 equals to V2, right? So this is, let's suppose, at time t equals to t1. Let's suppose this value is what, 10 meter per second. But at t equals to t2, this value gets changed. V1 equals to V2 equals to 15 meter per second. Are you getting the point? So as the time changes, velocity changes, but again location to location that value remains fixed. As the time changes, location to location that value will remain fixed. But always remember, at any particular instant of time we are checking this particular thing, whether fluid properties are same or different. I hope this point is clear. Right, so you should aware of this point, like at any particular instant of time. Correct? Now, second is just opposite of this uniform flow. So in this case, what will happen? Fluid properties will change from location to location. Okay, fluid properties will change with respect to location at any particular instant of time. This point. right? So this is what a very basic things. I hope steady flow, unsteady flow, uniform flow and non-uniform flow, it is clear to everybody, right? Very basic things, right? Before going into the analysis part, we should be aware of such types of fluid flow. Then only we'll be able to understand, okay, if it is given in the question uniform flow, we should understand what actually uniform flow means. If it is given like steady flow and uniform flow, so that combination we should be have some knowledge about that combination. What actually it means, we should aware of those things. Then only we can do the analysis, right? Next, laminar flow, very important guys, very important. So usually this laminar turbulent flow, basic definitions at least you know, because see, separate chapters are there in the fluid mechanics subject. Laminar flow you will have a separate chapter and turbulent flow you will have again separate chapter, but at least basic definition you should be aware of, right? Before going to the individual chapter in detail about the laminar and turbulent flow, you should be aware of the basic meanings of laminar and turbulent, right? So see, what is laminar flow? So it is basically characterized by what? Very important point. By a smooth flow of one layer of fluid over an adjacent layer. A smooth flow of one layer over an adjacent layer. Very important. Smooth flow will be there. Smooth flow will be there and the movement of the fluid will be in terms of layer by layer. Layer by layer formation will be there and fluid will be what? Completely flowing. Non-uniform flow. See, Pragya is asking for non-uniform flow. See, simply whatever example I have given you, like let's suppose this is the nozzle you are having. Okay, so as the fluid flows through this nozzle, can you tell me the velocity will remain constant or it will change? Tell me. Will the velocity will remain constant or it will change or it will vary? What will happen? From section 1 to 2, velocity value will remain same or constant? It will remain same or it will vary. What will happen? So obviously it will change, correct? If it is changing, so it will a uniform flow or non-uniform flow? If it is changing, so then it is what? Uniform or non-uniform flow? Easily you can say, just now we have discussed, fluid properties do not change with respect to location, but in case of non-uniform flow, fluid properties change with respect to location. So obviously it is a non-uniform flow, right? As V2 will be greater than V1 in this case. So velocity along the flow, it is what? Increasing, and velocity, basically velocity value is going to what? Change along the flow. So it is the example of non-uniform flow. Now as you say about as you are asking about like steady flow, most of our engineering devices are coming under the steady flow. Most of the engineering devices are coming under steady flow. Asking about steady plus non-uniform flow. So I can give you, this is only the example of steady plus non-uniform flow. So let's suppose if you consider any particular time, this value what remain fixed. So let's suppose this is a nozzle. Okay, let's suppose this is a nozzle installed in any hydraulic turbine. Okay, in any hydraulic power plant or any steam power plant, this nozzle is there. So if at the entry the values are what? Fixed with respect to time, so it becomes a steady flow. And obviously if it is passing through nozzle, it becomes a non-uniform flow. So it is just an example of steady plus non-uniform flow. But you should remember this point, most of our engineering devices are under steady flow. They work under steady conditions. They work under steady condition. And if you remember in thermodynamics subject, if you know about little bit about the thermodynamics, most of the engineering devices are known as steady flow devices. If you have ever heard about this steady flow device, you get to know about those things. So please refer to the thermodynamics also. Like in the thermodynamics, we study the steady flow devices. So those devices work under steady conditions. But it is a uniform, non-uniform, it depends upon the given device. Okay. Now, so as we are discussing about the laminar flow, so very basic definition of laminar flow is what? The fluid flows in layers and one layer is what? Moving over another adjacent layer. So that is what the basic definition of the laminar flow. Second point. Okay, second point, very important point. Fluid particles move in a well-defined path. Okay, very important, well-defined path. So in the case of laminar flow, you can identify, you can have a picturization or graphical representation like fluid flowing in this path. So you will have a well-defined path. Okay, you can see the particle, how it is what moving. You can have a proper well-defined path for the fluid in the case of laminar flow. Okay, this point very important, the well-defined path, and also the movement of the fluid in terms of what? Layers, right? So this point you should always remember. Third point, very important. The laminar flow is also known as viscous flow or the streamline flow. We'll discuss what is streamline, right? But till now you should at least understand this point, like laminar flow is also considered as a streamline flow and it is what? A viscous flow. So because this laminar flow, you will see mostly in those cases where the viscosity is high or the velocity is what? Very low. Okay, I hope the point is clear, everyone, right? So these 3 points are what? Very important. Okay, so for example, generally what happens in a highly viscous liquids, in highly viscous liquid flows, you will see the laminar flow, and where the velocity of flow is what? Very low. In that cases, you will see the laminar flow, right? So this point is what? Very important. Now, after completion of this types of flow, we will be discussing regarding the fluid flow patterns, in which I will be discussing about the streamline, path line and the streak line, correct? Next. Now again I will show you the diagrams also with regards to laminar and turbulent, so that you will have a better understanding. Now when I say turbulent flow, very important point guys, very important. Here the fluid flow is what? Totally random. Randomness you will see, disordered flow you can say. Previously in the laminar flow, what is there? Well-defined paths are there, but in the case of turbulent flow, you cannot say about the fluid is having a well-defined path, right? Totally zigzag manner is there, okay, or even you can say disorder manner. Okay, so this point you should remember, disorderly manner or the zigzag manner. Zigzag basically represents what? The disorderness or the randomness, right? Second point. And because of this disorderness, what will happen? Rapid and continuous mixing of the fluid particles, because there is what? The randomness or the disorderness within the fluid flow. What will happen? Mixing of the fluid particles. And if the mixing of fluid particles is there, you can understand a very important point. As the fluid particles is moving here and there, momentum transfer will be what? Very high. Momentum transfer will be what? Very high in the fluid flow. Very important point, very important. Okay, and the last point, eddies and the vorticities. Okay, eddies and the vortices are formed in the turbulent flow, which causes the energy losses. So very important. So eddies are basically what? The circulatory movement of the fluid. Okay, circulatory movement. So these eddies, you should remember this point. Okay, eddies are what? Very important point here. So this circulatory movement of the fluid flow, right? So this disorderness will have more energy losses. Okay, more energy losses you will see in this particular case of fluid flow. So very important point guys, disordered flow. Okay, totally randomness you will see in this flow, and as the fluid particles are moving here and there, so more momentum transfer will be there, right? So this point is what? Very important. And if you compare this with the laminar flow, what will happen? Well-defined paths are there and the fluid is moving in layer form, not the fluid particles is moving from one layer to another layer, right? This will not happen in the case of laminar flow. Now from this diagram, at least you will be able to understand like how the laminar flow is there. Simply you can see the well-defined paths are there, and here there is no well-defined path. Are you able to understand this point? From this figure you can understand this basic point. Well-defined path in the case of laminar flow. Well-defined path. And in the case of turbulent flow, what will be there? Disorderedness you can see. disorderness you can see, and the fluid particles is moving randomly here and there, and obviously the momentum transfer will be happening. Now it is not necessary that always in the case of laminar flow this path will be straight line. No, it is not like that. It can be in the curved form also. So just for simplicity I am showing this particular diagram so that you can understand a well defined path in the case of laminar flow, and you cannot see the well defined path in the case of turbulent flow, right? I hope the point is clear, everyone. Please tell me first. Okay, Pragya. Okay, great. Now next thing, I hope you have seen this particular thing practically also. Lot of time you have seen this particular case. Right now I will tell you the main difference here. So usually when you have this candle, let's suppose you are having a candle and you have just lighten up this particular candle. So usually initially you will see what a perfect fluid particles for particular well defined path you will see. Initially you will see a well defined path for the fluid particles, obviously the particles which is coming out from here. So well defined path you can see up to certain distance, then after that there will be some disturbance you will see, that is actually the transition phase, and after that you will see entire randomness you will see. So this type of things you will be what observing everywhere. Even let's suppose you are having a tap here. So if you just open a tap for some distance, let's suppose for some distance you will be having a laminar flow. And why I am saying a laminar flow? Because you will see a well defined path, well defined flow you will observe, right? And later you will see some transition, and after that some turbulent disorderness you will see. So just from practical observation you can understand this phenomena also. So this is a case of a candle, and this is a case of, let's suppose, a tap I am taking. So initially well defined path you will see laminar, then there will be some transition phase, and after that complete disorderness or randomness you will observe. Are you getting the point? So this is what the practical observation, from the practical observation we can understand this thing. So laminar, then transition, and the turbulent, and we'll discuss this thing in more detail in chapter fluid boundary layer. In fluid mechanics there is a separate chapter like boundary layer, in that we'll discuss in detail. But as of now, from the practical observation you can understand this phenomenon also. Just I've taken the example of the tap, okay, and I've taken the example of this candle. So initially well defined flow you will see, and after that some disturbance, and after that complete disorderness, complete randomness you will see. I hope the point is clear, everyone, right? Okay. Now next point, guys, see, compressible and incompressible flow, very important. In case of compressible flow, what is the basic meaning of compressible flow? Density of the fluid flow, what will happen? Does not remain constant, right? But in the case of incompressible flow, density will remain constant. So this point you should understand, like density is not constant in case of compressible flow, and here in this case density will remain constant. So when I say density does not constant or remain constant, you should be aware of the point, like during the fluid flow I am considering. During the fluid flow I am considering this phenomena, because compressible flow I am saying na. So for a fluid flow, when a fluid is under motion, I am just checking the density. Is there any variation in the density when the fluid is what flowing or not? That point I need to check. So during the fluid flow, if the density is going to change, then it becomes a compressible flow. And if it is not changing during the fluid flow, it becomes an incompressible flow. So this point is again very important, and we'll see the conditions under which there will be compressible or incompressible flow. We'll see those conditions also later in this chapter only. We'll see the conditions, but as of now you should be aware of the meaning or understanding of this particular term, compressible flow and incompressible flow. We'll discuss the criteria under which it is valid. Like, these are the conditions, these are the parameters, these are the conditions, compressible flow will be there. So those points you will be able to understand after few lectures, right? So obviously in the later lectures we'll be discussing the conditions of the compressible flow and the incompressible flow. Okay, so don't worry about that, but just understand the meaning of this type of flow. Now, so this is one image for you. Can you tell me what is the difference between this figure and this figure? So let's suppose this is figure number 1 and this is figure number 2. So what is actually the difference between figure 1 and figure 2? Can anyone please tell me what is the difference between figure 1 and figure 2 with regards to type of flow? With regards to type of flow, can anyone tell me what is the difference? Please try to answer this particular question. What is the difference between case 1 and case 2? So this is what actually a velocity profile. If you see na, this particular thing, this is a velocity profile. Okay, we'll also see how this velocity profile is coming in the pipe. We'll discuss those things later, right? But as far as this curve is there, it is what the velocity profile. We'll discuss the reason why it is so, why it is like this only. We'll discuss those things later. But can you tell me what is the difference between case and 1, 2? Uniform and non-uniform flow in the radial direction. See, very important point. So let's suppose if I ask you the 1D flow, 2D flow, what is 1D flow and 2D flow? One-dimensional flow, two-dimensional flow. So see, when I say one-dimensional flow, it means properties are a function of one dimension. Properties are a function of one dimension. But when I say 2D flow, properties are a function of two dimensions, like x, y. In the case of 1D, it will be a function of only one of the directions, one of the dimensions. Now, in case 1, try to understand this point, very, very important point. Velocity is going to vary only with respect to radial. Only in the radial direction, velocity is going to change. Along the length of the pipe, velocity is not going to change. So, velocity is a function of r in the case of, in the first case basically. But in the second case, velocity is a function of r as well as the distance x, because it is what having a converging shape for this pipe. So velocity is a function of x as well as r, but in this case velocity is only a function of r. So it is an example of 1D flow, or I can say it is an example of 2D flow. Are you getting the point? Yes or no, guys? Please tell me. Is this point clear? So you should be aware of such things also, right? So what I will tell here, like velocity is a function of r, but here in this case velocity is a function of x and r. Okay, clear everyone? Okay, got it. Okay, great. So till now we have discussed the various types of fluid flow. I hope all those fluid flows are clear to everyone. Regarding other fluid flows like rotational flow, irrotational flow, we'll discuss later in this chapter only, because for that you should be aware of the term like what is rotation in the case of fluid flow. How we can measure those rotationality points, how we can measure those things, how we can quantify those things. You should be aware of those parameters. So that's why I will be discussing like what is rotational, irrotational flow later in this unit only, right? So whatever we have discussed regarding types of fluid, like types of fluid flow, example 1, steady flow, unsteady flow, uniform, non-uniform, compressible, incompressible, laminar and turbulent, all those basics we have covered till now, because this much basics at least you should know. Now we'll move on to the types of fluid flow pattern. Okay, fluid flow pattern, very important point guys, very important. Now when I want to analyze the fluid flow, I need to know how the fluid particles is what flowing. What is the pattern of the fluid particles during its motion? I need to understand how the fluid particles is what flowing. Is there any pattern that I can check or that I can figure out just by observing the fluid particles? So actually, in order to visualize the fluid flow, we have scientists has basically come up with few lines. Some are the actual lines, some are the imaginary lines. But you should understand these lines are actually used to visualize the fluid flow. If you really want to visualize the fluid flow, these lines will help you out. These lines will help you. So whatever under fluid flow pattern, those lines that I am discussing here, those lines will basically help you to understand the flow visualization. It will help you out in the flow visualization. So flow visualization is what very important whenever we are going into the analysis of fluid flow, right? So fluid flow pattern we'll be discussing. See, first of all, streamline. Yes, in CFD analysis also, very important point. Computational fluid dynamics, right? Very important point. But see, that CFD is on another level, right? CFD is what on another level. Because actually what happens, we are doing analysis for, let's suppose, any particular point, right? By applying the equations of motions. For one particular point we are doing the analysis. But for entire flow field, let's suppose I have to do the analysis. For that, one individual cannot do so much calculation. For that we need what? Softwares like CFD. They will do the calculation. You will just give the inputs. They will do the calculation for you. So you should understand this point, very important, right? So for one particular point in any section, I can do the calculations. But for entire flow field, I cannot do the calculation on my own. I need some help. For that, such softwares like CFD will help you out. Right. So now what is streamline? Very important guys, very important. Streamline may be defined as the imaginary line. First of all, you should understand this is imaginary line. Okay, it is not in actual terms. It is just an imaginary line, just it help you to visualize the fluid flow. It is not in actual terms. It is an imaginary line, very important point. Okay, drawn through a flowing fluid in such a way that, what is the condition? Now this condition we have defined. So if it is imaginary, I can define that streamline like in my own terms, na? It is an imaginary line. I can define my streamline according to my terms, right? So what they have chosen, what is the condition of the streamline, right? They have defined in such a way that tangent, if you draw the tangent to it, if you draw the tangent to that particular line, what actually you will be getting? You will be getting the velocity of flow at that particular point. So actually what happens? Now see, very important point guys. So let's suppose this is the flow field, very important point, please try to understand. This is the flow field. Okay, let's suppose any point I have selected here. Let's suppose this is my point. So if this is my point, at this point, let's suppose my velocity is like this. So direction of velocity is like this. And let's suppose at this point, velocity is like this. Okay, and this point, the velocity is like this. Now, at different points, I have figured out the direction of velocity. So it is my flow field. Try to understand what is flow field. This is my flow field. At every point in the flow field, I have defined the velocities. Now, what I will do here, I will just join these points, right? Assume these points are what? Very close. I've just joined these points, right? I've just joined these particular points. And on this line, if I draw the tangent, so here I have drawn the tangent like this. Let's suppose here, if I have drawn the tangent like this. So again, what I will be getting? The velocity vector. right? So these points at least you should be aware of. So in the flow field, at every point you will be having the direction of velocities. You will be having the direction of velocities, right? So those points, let's suppose they are very close to each other. If those points are very close to each other, we can draw the line. Okay, we can draw the line. So that is what a streamline here. Again, remember, it is totally a imaginary line and it is defined in such a way that, what is the condition? It is defined in such a way that if you draw the tangent, you will be getting the velocity direction. You will be getting the velocity direction. Very important point. So it is for us, like we have defined, we have given the definition of streamline. It is not physically available in the nature, right? We have used this particular line. We have created this line just in order to help us to visualize the fluid flow. See, again, very important point, Pragya. Like if it is imaginary, then how we are drawing? See, that is what I'm saying, na? Like if it is imaginary line that I have understood, like I have picturized. Let's suppose I want to draw any line. Let's suppose any line I have drawn. Very important point. Now, you are saying, sir, it is imaginary and you are drawing also. Correct. It is imaginary because you cannot observe that particular line in the fluid flow. This line helps us to visualize the fluid flow, right? But actually, let's suppose fluid is flowing in a river. Can you say, sir, this is the streamline? Tell me this point. Can you say, sir, this is the streamline? No, it is not possible. No. So that's why we are saying it is imaginary. Are you getting the point? It is imaginary because you cannot see that particular line in the fluid flow. You cannot see. Right. Now see, I will show you the diagram here, and from that diagram it will be clear to you. See, very, very important. Velocity field around, let's suppose this is a cylinder and across this cylinder fluid flow is there. Across the cylinder there is a fluid flow, right? Now, as the fluid is flowing, at every particular point you will be having some velocities. So at this point this is the velocity, at this point this is the velocity, at this point. So whatever points I am drawing, for that arrow shows the direction of velocity. So this is the flow field. In the flow field I am just drawing the points. So whatever points I am drawing, for that whatever arrow is there already in the diagram, those arrows shows the direction of velocity. Now see this diagram and see this diagram. Streamlines for ideal fluid flow around the cylinder. Now actually why it is called imaginary? You cannot observe the lines practically. You cannot observe the lines. That is why it is called imaginary. I hope the Pragya point is clear. That these lines you cannot observe. While actually observing the fluid flow, you cannot see these lines. Right? So these lines you cannot practically observe, right? But you can draw these lines so that you will get to understand, okay, this type of fluid flow is there. Okay, the fluid particle is flowing like this over the cylinder, and below the cylinder it is flowing like this. So these are what very important points. So whenever I'm saying like fluid kinematics, I see this point initially you told like, sir, it is very difficult. So it is difficult because we are not able to visualize how the fluid flow is there. We are just remembering the theories and the formulas. You need to understand through diagrams and the graphics. Okay, so that's why the graphics and this picturization is also what very important. Otherwise you will just remember the theory, and in practical life you have never seen how these streamlines are drawn over the fluid flow, and if we are drawing those streamlines, it is helping us to understand the topic of the fluid flow pattern. Correct? So I hope this diagram helps you a lot in understanding of the streamline. Next, path line. Now if I ask path line, so it is what very basic, very easy. So we will basically trace a fluid particle and we will observe its journey in the fluid flow. So whatever it is having, whatever path it is following, that particular path is known as path line. So let's suppose this is a particle. and if it is flowing like this, so it becomes the path line simply. Simply it becomes the path line. So you will just trace any particular fluid particle in a fluid flow. You will observe its journey. You will draw the path wherever it is goes. Okay, so like this it is moving. So like this it is moving. So you just observing the fluid particle, and throughout its journey you just observe. So whatever path you are getting, that is what the path line. Very simple. Okay, and it is what the actual path. Okay, it is what the actual path. Next, streak line. Very, very important, and here most of the students will have a confusion and they are not able to visualize this streak line. That answer you have to tell, Pragya. Path line is a Lagrangian approach or Euler approach. In the starting itself, I have told you what is the approach here. Two types of approaches we are having. I hope you have understood that point. If you have understood that point, you can easily tell me. In the starting of the lecture itself, I have told you. Now you should answer. Like if you are listening the lecture properly, then you should able to answer this particular point. And I hope you will give the correct answer only. Right? So where we are studying the flow pattern. Okay, streamline we have discussed, path line, and after that streak line. I am waiting for your answer, right? So see. Now first of all, okay, great. Now see the definition first of all, then I will give you example also. Through diagram only I will explain you how this streak line is there. So it is the line at any instant of time. First of all, at any instant of time, which is the locus. It is the line which is the locus of the temporary locations of all the particles. Of all the particles that have passed through a fixed point in the flow field. Okay, so it's my request, again repeat this definition, again read this definition. Okay, because it is what very important. In some books this definition has been given in more complex terms. So I have just simplified the definition here for you. In books, if you see the definition is what more complex, and even the diagram is much more complex. Yes, that answer you will give after the explanation. It is real or not, you will give me. So this answer you have to give. I will show you the diagram also here. But as far as this definition is concerned, you should be like clear. So at any instant of time, at any particular time, it is the locus. Locus of what? Locus of all the temporary location of the particles. Temporary locations of the particles which have passed through a fixed point in the flow field. Now first of all tell me, is the definition is clear? Yes or no? Definition is clear, yes or no? Please tell me. No, definition is not clear. Okay, then definitely it will be clear with the diagram. Now see, I hope you have seen the chimneys, right? So let's suppose I am drawing any chimney here. Okay, now from the chimney, so basically this is the exhaust point from which the exhaust gases are what coming outside. So let's suppose the particle came here like this. From this is the fixed point from which all the exhaust gases, all the exhaust particles is coming outside, right? Correct, everyone? Now see, try to understand very important point. So let's suppose at any interval of time, at any time, at any instant of time, you are observing the chimney. Correct? First of all, okay, at any instant of time you are observing the chimney here. So this line can be like, it can have any shape. So just I'm drawing any random shape. Okay. Now see, very important point. So at any instant of time you are observing. So let's suppose the particle which come from this fixed point, it has reached to this point, it has reached to this point, it has reached to this point, and let's suppose it also reached to somewhat here. So let's suppose it reached this point, this point, this point. Now please try to understand. So these blue dots, what are these dots? These are the particle which has come from this fixed point. All these points, all these blue dots are the particles only. Blue dots are the particle only which have come from this, which has come from this fixed point. First of all, you should understand this point. From the chimney, there is a fixed point out of which the exhaust particles are coming. So at any instant of a time, I am observing those particles. So let's suppose at any time I have observed like my fluid or exhaust particle reached to this point, another particle reached this point, another particle reached this point. Similarly, different are the temporary locations of the exhaust particles. Now, according to the definition, what is there? Locus of the temporary location of the particle. Temporary location of the particle. So blue dots are what? The temporary location of the particle only. So what I will do here, I will just draw a line connecting this temporary locations. I will just draw a line, or I will just draw the locus of all the temporary locations. Okay, so whatever I have drawn with the red color here, it is just the locus of all temporary locations of the particle which has come from this fixed point at any instant of time. So that particular line is what? The streak line. Now you are saying, sir, it is real or like imaginary. So have you ever observed like through the chimney? If you like passing through a chimney, you will see. So let's suppose this is a chimney, you will see like this. This kind of exhaust you will see. So it is real. Yes, obviously. But any particular instant of time, let's suppose at time t you are observing, and again you are coming after few hours, it will not be same. So let's suppose at time t you have observed, and after few hours you again come back and you will say, sir, again now it is not there. It will not be there obviously, because streak line is the locus of temporary locations of the particles which has come from the fixed point. Yes or no? Up to this point it is clear. So this diagram, so understanding of this diagram will be like this. So particle has come from this fixed point like this. So you have just joined the temporary locations. You have just joined the temporary location of the particles which has come from the fixed point. So that is what the streak line. And it will again, see why we are using this line? Because it will give us the visualization of the fluid flow. It will give us the visualization of the fluid flow. That is what we have practically observed in our life also. So I hope the path line, this streamline, the velocity field, okay, most important diagram, very important diagram, the velocity field and the streamline point. Okay, so these points are what very important. Okay, it is clear, right? Good, very good. So now see, we have discussed the type of fluid flow. We have discussed something about the fluid pattern also, like how we can visualize the fluid. When fluid is having motion, how we can visualize that particular thing. For that we are having three lines: path line, streamline and a streak line. So all those basic things we have already covered. Now in the upcoming lectures, I will be focusing on the velocity and acceleration of the fluid particle. Now in that lecture, mathematics is what totally involved. So if you have any difficulty, please again come live. We'll see all those important points. Whatever basic mathematics is required, I will be discussing that part also, so that you will have a full confidence over the fluid kinematics part. So in the velocity and acceleration part of the fluid particles, mathematics is involved. Okay, if you have any problems or any challenges you are facing whenever you study those topics, please come live in the upcoming lecture. We will discuss that topic from the scratch, right? So I hope in this lecture you have understood about the fluid flow, what is kinematics is all about, what is the fluid pattern, right? So I will meet you in the next lecture and we'll start the velocity and acceleration analysis of the fluid flow. Thank you so much.